Hi guys. Today I'm going to explain how the kidneys filter blood, how solutes and waters are reabsorbed, how GFR is regulated, and how hormones like ADH and aldosterone influence kidney function. I'll also explain how the loop of Henle creates a medullary concentration gradient and how this allows the body to produce the concentration or diluted urine. So that is all we're going to be talking about today. So first, we're going to talk about the filtration, reabsorption, GFR, and hormones. So we're going to talk about filtration in the renal corpuscle. Here is the renal corpuscle. Filtration takes place here. This is in the glomerulus, and filtration takes place in the renal corpuscle, which is this whole thing. And that includes the glomerulus and Bowman's capsule. Blood enters the glomerulus through the afferent areolus, so right here, and the high pressure inside the capillary forces the fluid into a small solutes out of the blood into the Bowman space to form a filtrate. The filtrate membrane has 3 layers. The first layer is fenestrated endothelium. The second one is fenestrated endothelium of the glomerulus capillaries, which has pores that allow water and small solutes to pass, but not blood. The second layer is the basement membrane, which has negative charges that helps repel most large proteins. And the third is the podocyte filtration sites, created by foot-like processes with slit diaphragms that act as the final filter. Together, these layers let water ions, glucose, and amino acids pass while keeping proteins and cells in the blood. Filtration is driven by several pressures. The main force pushes fluid out of the glomerular hydrostatic pressure, which is about like 55. There are two forces. There's the capsular hydrostatic pressure, which is about 15, and the blood collated osmotic pressure, which is about 30. When you subtract the forces pulling the liquid into and out, you are getting the net filtration pressure, which is about 10, which moves filtrations into the Bowman's capsule. That is all right here. My beautiful drawing. Okay. Regulation blood flow to the glomerulus. The kidneys are tightly controlled by GFR. By adjusting the diameter and the afferent and efferent arterioles, if like the afferent arteriole dilates, the more enters the glomerulus and increases GFR. If the afferent arterioles constrict, less blood enters and GFR decreases. If efferent arterioles constrict, the pressure inside the glomerulus rises and the GFR increases. If it dilates, the pressure drops and the GFR decreases. This regulation happens through just autoregulation, the sympathetic nervous system working, and then hormone regulations like RAS. Glomerular filtration rates. The GFR is the amount filtered formed per minute and is normally about 125 microliters per minute. It is used to assess kidney function. Clearance is a concept that uses the estimated GFR. It tells you how much of the plasma is cleared of a substance. If the substance is freely filtered and not reabsorbed or secreted, its clearance equals the GFR. Creatinine is commonly used because it is commonly produced by muscles and filtrated by the kidneys. Although the small amount is secreted, creatinine clearance gives a good estimate of GFR. The tubuloglarial feedback. The tubuloglarial feedback involves the macula densa and the group of distal cells. These cells sense the amount of sodium and chloride in the filtrate. If sodium chloride levels are high, this means the GFR is too fast, and the macula densa triggers the afferent arterioli constriction, reducing GFR. If there are low levels of sodium chloride, this means that the GFR is too low. The macula densa signals the afferent arterioles to dilate and also stimulate the release of renin, increasing GFR. Reabsorption in the kidneys. Once the filtrate enters the tubules, which are these things right here. Once it enters the tubules, the kidney reabsorbs most of it. Roughly 65% of the reabsorption occurs in the proximal convoluted tubule, which is this one right here. The reabsorption, sodium is a key driving force for reabsorption. Inside the tubule cells, you have sodium concentration, and it's kept low by the sodium-potassium ATPase pump. This moves 3 sodiums out and 2 potassiums in. Because the sodium is low inside the cell, sodium easily enters the tubular fluid. And the way the sodium enters is by antipores, which is like there's a channel that will push a sodium in and a hydrogen out, or co-transporters that will bring glucose or amino acids out with the sodium. And we can see that here. We have the sodium coming out with the glucose, that one coming out with an amino acid, and then your sodium, potassium. And then something I forgot to draw here was I don't like that. ATP, because it uses ATP. Yeah. Reabsorption of glucose. Glucose is reabsorbed in the PCT, where we were just talking about, and that uses secondary active transport. Glucose enters the cell through the sodium GLT2 transporters on the surface level of the cells through the GLUT transporters on the biolateral side. However, glucose transporters can become saturated. This leads to the concept of renal threshold, that if glucose exceeds past a certain amount, then it won't be able to keep up, and then there'll be glucose in the urine, and that is how they tell diabetes. And when we talk about that, we see a graph that kind of is like that, and right here would be your renal threshold. It's up, and then line right here would be your renal threshold, because it's just, you can't hold any more of it. Amino acids are reabsorbed through sodium-dependent cotransporters. They are almost completely reabsorbed. Water moves 2 ways. It moves through facilitative water reabsorption, which is like aquaporins. Those are controlled by ADH. It occurs in collecting ducts, and they let water out. Then you have another type that happens in the PCT. It's for sodium. It's for the osmolarity, and it's not really influenced by anything. I think it is influenced by the angiotensin 2. But yeah. And reabsorption of chloride. It is through the NKCC2, which is sodium, calcium, and that one's in the loop of Henle. Then reabsorption of potassium. is through the NKCC2 as well in the collecting duct. The potassium can be secreted, and that can use it uses aldosterone to secrete it. The reabsorption of calcium, same place. It uses a parathyroid hormone, PTH, to become reabsorbed. Okay, so we're gonna talk about like RAS. You have the kidneys that release renin, and then renin converts to agnotensin 1, then to agnotensin 1, then ACE converts agnotensin 1 into agnotensin 2, and agnotensin 2 causes vasoconstriction, rise in blood pressure. It constricts the afferent arterioles, stimulates aldosterone release, stimulates ADH, and increases thirst. That way you can drink more to create more volume. Aldosterone, it increases the number of ENaC, like sodium channels, and increases the activity of the sodium-potassium ATPase pump. ADH binds to the V2 receptors of the collecting ducts to trigger and insert aquaporins, and that allows water to be reabsorbed into the concentrated medulla, producing concentrated urine. So part 2 we're moving on to is right here, the loop of Henle. How the loop of Henle creates the medullary concentration gradient. Well, the descending part is permeable to water, but not permeable to solutes, and as filtration moves down, water leaves and making filtrate more concentrated. The ascending limb, which would be descending and then ascending. Descending. The ascending is permeable to water and actively pumps sodium, potassium, and chloride. It dilutes its filtrate and increases the osmolarity of the medulla. Together, these processes create a gradient. Urea recycling. Urea leaves the intermedullary collecting duct and diffuses into the medulla, helping maintain a high osmolarity. The gradient with ADH for urine concentration, the collecting duct remains impermeable to water. Water stays in the filtrate, and then the urine becomes very diluted. With ADH, though, you have more aquaporins, which then means more water, causing hyperosmolarity, which then makes the urine become very concentrated. That together allows the kidneys to produce anything from diluted urine when you're hydrated to very concentrated urine when you're very dehydrated. So let's go back and see if we covered everything. Yes. Perfect. Yeah. So if you guys have any questions, always feel free to reach out. But I think that's it for tonight.